Welcome to The Explainer. Today, we're diving headfirst into a really fascinating Katie Nuggets tutorial by Matthew Mayo, and we're going to see exactly how to give the Gemma 4 model local tools. Essentially, we're talking about taking a small, super lightweight language model and giving it the actual power to do things right on your local machine. It's pretty wild. Now, before we even write a single line of code, we have to ask ourselves a pretty crazy and honestly slightly dangerous question. What actually happens when you give an AI the keys to your computer? I mean, it's one thing to have a model summarize a text file you just paste into a chat window, right? But it is an entirely different beast when that model can just explore your file system and execute code all on its own. All right, here's exactly how we're going to break this down today. First, from chatbots to true agents. Second, building the safety perimeter. Third, Tool 1, the Filesystem Explorer. Fourth, Tool 2, the Python interpreter. Fifth, the orchestration loop. And finally, number 6, agents in action. Okay, section 1, from chatbots to true agents. So what do we actually mean when we throw around the word agency? Well, true agency kicks in when a model starts interacting with the very system it's running on. As Matthew Mayo points out, if you just give a model read-only web APIs, you still basically just have a chatbot. Sure, it has access to better, fresher information, but that's about it. But when a model can read a local file, run a script, or check what's actually inside a folder before making a claim about it, that is where real agency begins. The model suddenly has a tangible environment to reason about. This is a massive distinction. Think about it. Chatbots basically operate on a loop of fetching remote data and stitching it into a neat little paragraph. It's very much like standard retrieval augmented generation. True agents, on the other hand, have actual state. They inspect their local environment. They can ask themselves things like, wait, what does this calculation actually equal? Or what files even exist in this directory? And the really incredible thing here is that the Gemma 4 Edge variant is small enough to run entirely locally on a standard laptop, yet it's capable enough to drive this exact kind of complex, multi-step reasoning loop. Moving right along to section 2, building the safety perimeter. Because we are making this huge shift from hitting remote APIs to executing code locally, we absolutely have to put up some hard guardrails. The entire design problem changes here. We aren't just parsing JSON responses anymore. We are actively trying to ensure the model cannot accidentally or deliberately do something it shouldn't. Think about it. If the model can run code, it can theoretically delete your files or expose your sensitive data. So we have to build a strict safety perimeter right out of the gate, tightly restricting things like path traversals before we hand over any level of control. Section 3, Tool 1, the Filesystem Explorer. We're calling this first tool list_directory contents. It essentially gives our model eyes to see what files exist on the machine. Now look at these 4 steps. They perfectly outline a foolproof path traversal guard. If a model asks to look at a specific directory, a lazy implementation might just let it wander straight into your root directory or let it dig up your API keys using standard command line tricks like .. We don't want that. Instead, we literally never trust the string the model produces. We pin down a safe base directory, join the model's requested path to it, resolve it absolutely to strip away any trickery, and then explicitly verify that the final path still starts with our safe base. If it doesn't, the request is rejected immediately, no exceptions. Once that safety check passes, the tool confirms the path exists and outputs a clearly formatted plain English string. It specifically tags items as a directory or a file and even includes the byte sizes. This simple, clean structure is incredibly easy for the model to parse when it receives the data back on its second pass. It ensures the model understands exactly what it's looking at without getting confused. All right, Section 4, Tool 2, the Python interpreter. Next up, we are handing the model a heavily restricted Python interpreter. Now, why on earth would we do that? Well, because small language models are just notoriously bad at precise arithmetic and exact string manipulation. Instead of forcing the model to try and do complex math in its head, we're giving it a calculator. But, and this is crucial, it is a very restricted one. By completely replacing the built-in's namespace, we securely whitelist exactly what the model can use. So we allow helpful things like math and statistics, but we completely strip out dangerous functions like open, avow, or import. And here is a really clever part of the setup, handling empty outputs. We capture the standard output, meaning we grab whatever the model's code actually prints. But as you might know, small models often write out expressions and completely forget to print the result. If we just returned an empty string, the model would probably confidently invent a hallucinated answer. So instead, by handling the empty output branch, we return a specific error that literally tells the model to use the print function. It forces the model to try again and get the real hard data. Section 5. The orchestration loop. Okay, so how do we actually tie the brain, the eyes, and the calculator all together? We use a two-pass loop with a llama handling the heavy lifting. First, we send the prompt and our available tools to the model. If the model decides, hey, I need a tool for this, we intercept that tool_calls block. We then execute the requested function locally on our machine, safely behind our perimeter, of course. We take that result, append it to the chat history as a tool message, and then we re-query the model. Finally, Gemma 4 synthesizes a solid, grounded answer based on reality rather than just guesswork. Let's see this in Section 6, Agents in Action. Let's look at our first prompt. What is the standard deviation of these numbers, rounded to 4 decimal places? This is a classic problem. Small models usually fail miserably at this if they try to calculate it purely using their language weights. But with our local tool setup, it's a totally different story. Instead of hallucinating a bunch of significant digits, the model brilliantly recognizes its own limitations. It writes a deterministic Python snippet, calls the statistics.std function, rounds it perfectly, and reports the exact right answer back. It offloads the work entirely to the interpreter tool. It's exactly what we want to see. Okay, now for the ultimate test, a prompt that requires the agent to sequence both tools together. It needs to inspect a local folder, and then it needs to do some math based on what it actually finds in there. And you know what? The 2 billion parameter edge model handles it completely flawlessly. First, it uses the Filesystem tool to ground itself in reality, reading the actual file sizes. Then, it immediately calls the Python interpreter tool to sum those sizes up and convert them into kilobytes. Finally, it synthesizes the final answer. This right here is true autonomous agency, produced locally on a laptop, no GPU required. The model is autonomously deciding which question to ask of which tool. But wait, what about that safety perimeter we built earlier? Does it actually hold up? Absolutely. If you try to trick the agent into listing the contents of a restricted directory like /etc., it produces a hard denial message. If it tries to open a sensitive system file in the Python tool, it hits a name error because remember, we entirely stripped out the open function. Crucially, these failures degrade gracefully into useful error strings that the model can actually read, rather than just causing silent compromises or crashing your whole system. Matthew Mayo wraps up the tutorial with a fantastic point. The true power of an agent unlocks only after you've safely defined its boundaries. Once that perimeter is completely secure, a file system-aware tool and a code execution tool get you most of the way to a genuine, highly capable agent, one that can observe, decide, and act deterministically. So the final question for you to consider today is this. Now that you know exactly how to build the perimeter, what will you let your local agent touch? Thanks for joining me on this explainer, and I'll catch you in the next one.